Hello, everyone. Welcome to our Deep Dive podcast, where today we'll be reviewing the paper WAN, Open and Advanced Large-Scale Video Generative Models from the WAN team at Alibaba Group. Are you ready to explore the next frontier in video generation technology?
Absolutely. This paper is a comprehensive report on WAN, a suite of open-source video foundation models. It's exciting because it not only pushes the boundaries of generative video models but also emphasizes openness and community contribution. Shall we start with the motivation behind WAN?
Yes, let's do that. The paper begins by highlighting the rapid advancements in video generation, especially after OpenAI's Sora. However, the authors point out that there's still a significant gap between open source and commercial models in terms of performance, capabilities, and efficiency. WAN aims to bridge this gap. Can you elaborate on the main challenges the authors identified?
Sure. The three main challenges are suboptimal performance of open-source models compared to commercial ones, limited capabilities. Most models only handle basic text-to-video tasks, and insufficient efficiency, making them impractical for teams with limited computational resources. WAN is designed to address all three.
That's right. WAN introduces several innovations, including a novel spatiotemporal variational autoencoder, scalable pre-training strategies, large-scale data curation, and automated evaluation metrics. These collectively enhance both performance and versatility. What are the key features of WAN?
WAN is characterized by four main features: leading performance, comprehensiveness, consumer-grade efficiency, and openness. The 14B parameter model, trained on billions of images and videos, outperforms both open-source and commercial models on multiple benchmarks. There's also a 1.3B parameter model that runs efficiently on consumer GPUs.
The openness aspect is particularly interesting. The team has open-sourced the entire series, including code and models, to foster community growth. This is a big step for democratizing video generation technology. Let's talk about the architecture. What's the core design of WAN?
WAN is built on the diffusion transformer DIT paradigm combined with flow matching. The architecture uses cross-attention to embed text conditions and incorporates full spatiotemporal attention for capturing complex video dynamics. The model is validated at scale, reaching up to 14 billion parameters.
The training data is also impressive. WAN is trained on billions of images and videos, amounting to trillions of tokens. This large-scale training enables the model to excel in motion amplitude, visual text generation, camera control, instruction adherence, and stylistic diversity. Can you explain the data processing pipeline?
Of course. The data pipeline is divided into pre-training and post-training stages. Pre-training data is curated and deduplicated from both internal and public sources, with a four-step cleaning process focusing on fundamental dimensions, visual quality, and motion quality. There's also a special focus on visual text data, combining synthetic and real-world text-containing images.
That's a thorough approach. For post-training, the focus shifts to improving visual fidelity and motion dynamics. High-scoring images and videos are further refined, and the dataset is balanced across categories like technology, animals, arts, and more. What about the dense video captioning process?
The team developed an internal caption model to generate dense captions for each image and video. This model is trained on both open-source and in-house datasets, covering tasks like celebrity recognition, object counting, OCR, camera angle and motion, fine-grained categories, relational understanding, and more. The caption model uses a LLaVA-style architecture with a VIT encoder and Quone LLM.
The evaluation of the caption model is also automated, focusing on 10 key visual dimensions. The results show that WAN's caption model performs comparably to Google Gemini 1.5 Pro, excelling in areas like events, camera angle, and style. Let's move on to the model design. What's special about the spatiotemporal VAE?
The WAN VAE is a 3D causal VAE designed specifically for video generation. It compresses the spatiotemporal dimensions of a video by 4 times 8 times 8 times, making it efficient and scalable. The architecture replaces group norm with RMS norm to preserve temporal causality and uses a feature cache mechanism for efficient inference.
The training of WAN VAE is done in 3 stages, starting with a 2D image VAE, inflating it to 3D for video, and then fine-tuning on high-quality videos. The feature cache mechanism allows for efficient encoding and decoding of arbitrarily long videos. How does WAN VAE perform compared to other models?
Quantitative results show that WAN VAE achieves superior video quality and high processing efficiency. Its reconstruction speed is 2.5 times faster than the previous state-of-the-art, and it handles diverse scenarios like texture, face, text, and high-motion scenes better than competitors.
Now, let's discuss the main model training. WAN uses a DIT-based architecture with 3 components: WAN VAE, diffusion transformer, and text encoder. The text encoder is UMT5, chosen for its strong multilingual capabilities and fast convergence. Can you explain the training strategy?
The training follows a flow-matching framework, starting with low-resolution text-to-image pre-training, then joint image-video training with progressively higher resolutions and longer durations. The training objective is to predict the velocity between noisy and clean latents using mean-squared error loss.
The model scaling and training efficiency section is quite technical. The main computational cost comes from the attention mechanism, which scales quadratically with sequence length. The team uses a combination of data parallelism, fully sharded data parallelism, and context parallelism to optimize training across large GPU clusters.
Memory optimization is achieved through activation offloading and gradient checkpointing, reducing GPU memory usage without sacrificing performance. Cluster reliability is ensured through intelligent scheduling and self-healing capabilities in the training infrastructure.
Inference optimization is also a highlight. Techniques like quantization, diffusion caching, and distributed computing are used to minimize latency. The model achieves nearly linear speedup on multiple GPUs, and diffusion caching improves inference performance by 1.62 times.
Prompt alignment is another innovative feature. The team rewrites user prompts using a large language model to match the style and detail of training captions, improving the quality of generated videos. This is especially important because user prompts are often much shorter than training captions.
For evaluation, the team introduces WAN Bench, an automated, comprehensive, and human-aligned benchmark. It covers dynamic quality, image quality, and instruction following, with 14 fine-grained metrics. Human feedback is used to weight the scores according to user preferences.
The results are impressive. WAN outperforms both commercial and open-source models on WAN Bench, excelling in motion generation, physical plausibility, image quality, and instruction following. Human evaluations and public leaderboard results confirm its superiority.
The ablation studies provide insights into the architecture. Sharing adaptive normalization layers and using UMT5 as the text encoder lead to better performance and efficiency. The VAE design also outperforms diffusion-based reconstruction losses.
Let's talk about the extended applications. WAN supports image-to-video generation, unified video editing, text-to-image generation, video personalization, camera motion controllability, real-time video generation, and audio generation. Each of these applications is backed by specific model adaptations and datasets.
For image-to-video, the model uses a mask mechanism to control which frames are preserved and which are generated. The dataset is carefully curated to ensure consistency between the first frame and the video content. The results show high-quality, dynamic video synthesis from static images.
Unified video editing is enabled by the Video Condition Unit, which integrates text, frames, and masks into a single input paradigm. The model supports tasks like in-painting, out-painting, extension, depth editing, pose editing, and more, all within a single architecture.
The text-to-image generation capability is a byproduct of the joint training on large image and video datasets. WAN generates high-fidelity images across diverse categories, benefiting from cross-modal knowledge transfer.
Video personalization is achieved by conditioning the generation process on user-provided face images in the latent space. The model avoids relying on external feature extractors, leading to better identity preservation and diversity.
Camera motion controllability is handled by encoding camera pose information and injecting it into the model through adaptive normalization layers. This allows for precise control over camera movements in generated videos.
Real-time video generation is made possible by the streamer approach, which uses a sliding temporal window to manage dependencies efficiently. Combined with latent consistency models and quantization, the model achieves real-time performance even on consumer GPUs.
Audio generation is another exciting application. The model generates synchronized soundtracks for video clips using a diffusion transformer and 1D VAE for audio compression. The results show superior long-term consistency and cleaner audio compared to baselines.
The paper also discusses limitations. Preserving fine-grained details in large motion scenarios remains challenging, and the computational cost of large models is still high. There's also a need for more domain-specific expertise.
In conclusion, WAN sets a new benchmark for open-source video generation. It combines state-of-the-art performance, efficiency, and versatility while being accessible to the community. The open sourcing of both large and small models democratizes video generation and paves the way for future innovation.
That's a great summary. WAN's contributions span architecture, data curation, training strategies, evaluation, and applications. It's a comprehensive effort to advance the field of video generation and make it accessible to everyone.
Before we wrap up, let's briefly touch on the contributors. The WAN project is a collaborative effort by a large team at Alibaba Group, with expertise spanning machine learning, computer vision, and large-scale systems.
And for those interested, all the code and models are available at https://github.com/WAN-video WAN2.1. This openness is a major step forward for the research and creative communities.
To summarize, WAN is a groundbreaking open-source video generation model that achieves state-of-the-art performance, efficiency, and versatility while fostering community-driven innovation through comprehensive open sourcing of code, models, and training pipelines.
Thank you for joining us on this in-depth review. We hope you found it informative and inspiring. Stay tuned for more paper reviews and discussions on the latest in AI research.
Goodbye, everyone.
Goodbye.